Okay guys, welcome back to fluids. Now, let's kind of remind ourselves about fluid dynamics. Remember, dynamics has to do with movement. So fluid dynamics is the study of the motion of fluids. And when we look at fluid dynamics, it all starts with the ideal fluid. An ideal fluid is one that fits the quote-unquote ideal model. So this fluid is incompressible, so gases don't count. The fluid is not viscous, which means it has a low resistance to flow. The fluid is steady. This is what we call laminar flow. The velocity of the fluid at all points in the fluid is consistent, okay? And when we have laminar flow, we have streamlines. A streamline is the path or trajectory a particle in the fluid follows. So let's look at a picture, okay? So these are streamlines, all right? So a particle would follow that trajectory. At any point along there, the velocity of the particles would be tangent to that line, okay? Now, another thing when you see streamlines is if the lines are closer together, you have a higher speed than when they're further apart. In laminar flow, streamlines don't cross. In turbulent flow, they would. Okay? So, a bundle of neighboring streamlines are called a flow tube. If a tube changes diameter, the volume of fluid passing through a region has to be maintained. So if the diameter of the tube changes, then the speed of the fluid has to change. Okay? So if I look at the speed V1 here and the speed V2 here, the speed at V1 has to be higher than the speed at V2 because the tube is bigger. Okay? The same volume of fluid has to be passing through that. So if the liquid here moves a distance, delta x, okay, then the distance that it moves down here, delta x2. Okay? The volume is V times A, surface area times the delta T. The fluid is incompressible, so these volumes have to be equal. Okay? So, the velocity times area 1 has to equal velocity times area 2. So that you can see that narrower tubes are going to have higher velocities. You'll also see people talk about the flow volume rate, which is Q. Q is equal to velocity times area. Okay, so we're going to look at problem 24 on page 471. So let me get to page 471. Actually, you know this book isn't going to do me any good. Hold on just a second, guys. I'm going to have to go run and get the book. Okay, guys, we're going to look at a problem here. And I've forgotten that they had changed this order of the questions in the book a little bit. So we're going to look at problem 26 here. Okay? It says water flows through a 2.5 centimeter diameter hose at 3 meters per second. How long minutes will it take to fill up a 600-liter child's wading pool? All right? Now, first off, let's start with the fact that we've got 600 liters. And a liter is not a SI unit. So I know that there are 1,000 milliliters for every 1 liter, and there's 1 centimeter cubed for 1 milliliter, and then let's see, 100 cubed, so that's 10 to, so for every 1 meter cubed there is 10 to the 6 centimeters cubed. So I can get this into meters cubed. So the milliliters divide out, 1,000 there, that takes that down to 3. So 600 liters divided by 10 to the 3 gives me 0.600 meters cubed. So our volume is 0.600 meters cubed. The other thing that we're told is that V, our velocity, is 3 meters per second, and that our diameter is 2.5 centimeters. So that's 2.5 times 10 to the minus 2 meters. So the radius is 1.25 times 10 to the minus 2 meters. So our area is pi times 1.25 times 10 to the minus 2 meters squared. Okay? Now Q, the flow volume, is going to equal V times area. Okay? So the Q that we've got, we need 0.600 meters cubed, has to equal the velocity, 3.0 meters per second, times the area, which is pi times 1.25 times 10 to the minus 2 meters squared. So let me grab my calculator. I can't do that in my head. So 3 times 1.25 exp to negative 1.25 exp to negative squared times pi times 3. So 0.60, wait a minute. Don't put that there, I'm getting Q. So Q is 1.47 times 10 to the minus 3 meters cubed per second. Now, it asks us to find time, delta T, to fill up the container. So I have 0.600 meters cubed is equal to 1.47 times 10 to the minus 3 meters cubed per second times delta T. So I get delta T to be 407 seconds. It didn't tell me that it wanted it in minutes or any other time unit, so we'll stop there. 407 seconds. Okay? So that's a use of our equation. Okay. Now, let's talk about de Broglie's equation. Okay? De Broglie is what we can base flight on. And it all is based on the fact that external work equals change in kinetic energy plus change in potential energy. Working with this, we can say that the pressure at a point 1 plus 1/2 the density times the velocity of the fluid squared at point 1 plus the density times acceleration due to gravity times y1 being its height, is equal to P2 plus 1/2 the density times V2 squared plus the density times G times Y2. Okay? This is the basis of Bernoulli's equation. Now, let's look at a picture. Okay? So, here we've got force due to pressure at point 1. Okay? We've got an area at point 1, and it moves at distance delta V. If it moves up here to a position 2 that's at a new height, we're going to have an area here and a delta X, okay? A volume A times delta X2. And we're going to have a different pressure here at point 2 because we're at a different height and we've got a different width of our tube. Let's roll it up a little bit. So we're going to look at a problem, okay? At the back of the book, we're going to look at problem 30 on page 384. it says, what does the top pressure gauge read in 14.40? So you can see there at the bottom, we've got 200 kilopascals, we've got 2 meters per second. At the top, we've got a speed of 3 meters per second, and it's a height of 10 meters. And it says we've got oil. Okay? Now, we're not given any other piece of information. That's it. So let's start working with this. So we've got a V1, 2 meters per second. Y1 is 0. And we are told that the pressure there is 200 kilopascals. That's 2.00 times 10 to the 5 pascals, because remember I need it in SI units. V2 is 3 meters per second. Y2 is 10 meters, and the pressure P2 is unknown. Okay? So we know that P1 plus 1/2 density times V1 squared plus density times acceleration due to gravity Y1 has to equal P2 plus 1/2 the density times the velocity at point 2 squared plus the density times G times Y2. Now, I need the density because this is oil. I looked it up, and the density here is 900 kilograms per meter cubed. Okay? So if I start plugging into this, P1 is 2 times 10 to the 5 pascals plus 1/2 times the density, 900 kilograms per meter cubed, times the velocity squared, as 2 meters per second squared. And this is going to be 0 because Y1 is 0. Has to equal P2 plus 1/2 times 900 kilograms per meter cubed times 3 meters per second squared plus the density, 900 kilograms over meters cubed times 9.80 meters per second squared times 10 meters. Okay, so let's start playing with it. Start running the numbers. So 900 divided by 2 is 450 times 2 squared, so that's 1800 plus 2 exp5. So over here I have 2.018 times 10 to the 5 pascals has to equal P2 plus 450 times 3 squared plus 900 times 9.8 times 10. So I get 9.225 times 10 to the 4 pascals. So solving for P2, I get 1.09 times 10, well, I actually am going to get 110 times 10 to the 5 pascals. My calculator is reading 1.0955 times 10 to the 5. If I round that to 3 sig figs, which your book always does, I get 1.10 times 10 to the 5 pascals. Or you could say 110 kilopascals. It didn't say what unit it wanted it in. Okay? So pascals or kilopascals, either one would work. All right, guys. Now, let's think about speed of moving air and pressure. Okay? All right. Now let's take a piece of paper. Take a piece of paper here. Let me see if I can get this demo to work so that you can see it here. Okay, now piece of paper is hanging down. Notice when I blow over the top, the paper lifts. That's because the air moving over the top, because it's moving faster, has a lower pressure. Okay? This is how an airplane wing works. When the airplane wing moves through the air, okay, roll it up for me. I want you to think about the streamlines. Here's the shape of a wing. Notice how it's fatter up here and it goes down. Well, when the air gets moved up over the wing, it actually gets compressed, okay? And when it gets compressed like this and we move to a smaller flow tube, the air has to be moving faster. The faster moving air has lower pressure. So you have higher pressure from slower moving air underneath, lower pressure for faster moving air up above, and that creates a net force upward on the wing, which is where you get your lift force. So this is how a plane flies. And every time I get on a plane, I keep going, I know Bernoulli's equation works. I know Bernoulli's equation works. I have to convince myself because I know that I'm in a very heavy object that's going to go sailing through the air. And I know about gravity. Okay? So the pressure beneath the wing is approximately atmospheric pressure, but the pressure above the wing is less than atmospheric pressure and you get lift. So let's look at stop and think problem on 378. Okay, the problem says rank in order from highest to lowest the liquid heights in the column. Okay, where it's moving faster, you're going to have the lowest pressure, which means you're going to have the lower column of liquid. If there is no flowing air in here, all of these heights, H1, HA, HB, HC, HD, are going to be the same. Here we've got essentially a Bernoulli's tube, where we're changing the cross-sectional area of the tube, and it's all at the same height. The center of this tube is maintaining the same height. So the only thing that's different here is the speed of the air due to the change in diameter of the tube. So if you look at it, the tube is narrowest here. That means the air is going to have to move the fastest. So the pressure above this section is going to be the lowest. So I'm going to have the lowest height. Okay? When it comes into here, we've got a big expansion. When we get to here, it contracts a little bit. This is the next widest section of pipe. So this one's going to have the next highest height of liquid. Here in the middle is going to be the broadest. Okay? So between B, C, and D, B is going to have the lowest height, D is going to be next, then C. And then out here, okay, this would be one where we have no airflow. This one's going to be the highest. This one's going to be atmospheric pressure. So it's going to go B is the lowest, then the next lowest is D, then the next lowest is C, and the last is A, because these have air streams going over them. Now, why aren't they the same?
They all look the same.
Well, they're showing you what it would be if there is no airflow. The minute you start the airflow, these things start changing. Now, guys, you can try this at home. Take a straw and put it in a liquid and blow over the top of the straw, and you can see the liquid lift in the straw. So this is something you can try at home. You can also do the paper trick, okay? So you can do both of those. Yeah. So, now, guys, I wanted to tell you, don't worry about sections 14.6. And I would like you on your own to look at example 14.11 and 14.12 in your book. And that ends chapter 14. And we will be starting, the next thing we'll do is chapter 15, and that's the last thing in the semester.